Now that we know separable equations and how to solve them, we can apply them to a variety of applications. I'm going to focus on two here. One of which is actually like the fundamental first task of kinematics. If you go to take Physics 410, then the differential equations that we're solving here are explicitly what we're talking about here in order to develop some equations for tracking the motion of an object in free fall. So one really important assumption here is that there's going to be no air resistance. So you can imagine that there's a mass, maybe a ball of some sort, mass m, that's falling, okay? And so it experiences exactly one force here, which is the force of gravity. And we put a negative sign as a convention to indicate that the force is pulling it downward. And the magnitude of that force is the mass times the acceleration due to gravity, which is g. Okay? So the typical IVP that gives you this. So we're going to, our task here, find the velocity formula as a function of t. Okay, given an initial velocity v of 0 equals v naught. Okay, so v naught, it could be positive, it could be thrown upward, it could be thrown downward, it could be starting from rest, which would be 0. Okay, and so really what we're talking about here is because of Newton's second law of motion, we're talking about solving the IVP mv prime equals negative mg subject to v0 equals v naught. Okay, so this is a first order equation. I'm going to show you in a second that this is in fact separable. In fact, it's even nicer than separable. It's really easy. So the actual dE here, mv prime equals negative mg. Notice that m cancels out. So if we divide both sides by m, we just get v prime equals negative g. Okay. In other words, dv over dt equals negative g. And we know that this must be true because this statement is just saying that the acceleration, let me try to write this better. Acceleration downward and equal to 9.8 meters per second squared. Okay, that's all this equation is saying. But if we then try to solve this separable equation, notice that the right-hand side, okay, doesn't have v or t. This is constant. Okay, so naturally, if we set up our differential form and then integrate, so on the right-hand side, we're going to get v, and on the left-hand side, we get negative gt plus c, okay? Now all we have to do is apply that initial velocity condition to get the full equation. So if we use v of 0 equals v naught, then we get v naught equals negative g times 0 plus c. In other words, v naught equals c. Well, isn't that crazy? Okay, so then, all told, so v of t, it's a function. Sorry, I want to make that a clearer t. It's going to be negative gt plus v naught. It's a linear in t, okay? Which means that if we want to imagine the graph of the velocity, right? If we start at some, I don't know, v naught, that's positive, right? And it's going down by exactly negative g per unit. So at some point, it reaches 0. And in fact, at some point, if you keep going rightward in t, right, it becomes more and more negative. without bound. So no matter what your initial velocity is, it eventually will be negative and continue to get more and more negative. So using this model says that with no air resistance, an object in a free fall is just going to continue accelerating faster and faster and faster, and then its velocity downward is unbounded. It's infinite. Okay. All right. But here's another model that we would talk about in kinematics. An object in free fall with a linear drag regime. By drag, we mean air resistance, or it could be any fluid that you're traveling through, but typically air, okay? So in this case, right, so we're going to assume that we have a ball again. Has some mass m, and it's still subject to this force of gravity, negative mg, but it's also going to be subject to this drag force equal to negative kv, or sorry, not negative kv. We're going to use kv. Or is it negative kv? Because we want it to go against the velocity. So no, it is negative, sorry. Yeah. So in this case, the negative means that it's going against the velocity, and because it's typically moving downward, then it actually ends up being a positive. So don't get fooled. Don't get fooled. Actually points upward. If this diagram doesn't make sense to you, it's a free body diagram, or a really crappy one. But we're just expressing the forces, okay? And so what we're going to see is that the drag counteracts the gravitational force, and so it'll slowly decay to some terminal velocity. Okay, so really what we have here is we have the dE, or sorry, the IVP. We're going to solve mv prime equals negative mg minus kv, subject to v naught equals, sorry, v of 0 equals v naught. Okay. To make this simpler on us, okay, for simplicity, let k equal 1 and m equal 1, okay? So really what we're going to have is v prime equals negative g minus v, and v of 0 equals v naught. Okay, so let's work with that. So we have the dE, dv dt equals negative g minus v. Is this separable? I contend that it is. Why? Because there is no t here, okay? So we can divide both sides by, basically we're going to divide by negative v plus g, okay? So then we're going to have dv over v plus g equals negative dt, okay? And that differential form is really just going to set us up for integrating with respect to v on the right side, on the left side, sorry, and with respect to t on the right side. And notice that this is going to give us ln of v plus g equals negative t plus c, okay? So not bad, okay? It's not too complicated so far. And actually, yeah, we can isolate at this point, or we can apply the initial value. So applying v of 0 equals v naught, we get ln of absolute value of g, which actually we don't need that at this point anymore, but in times 0, negative 0 plus c. So c equals ln of g, okay? which has a specific numerical value, right? Remember that this is equal to, or roughly equal to, the natural log of 9.8 meters per second squared, blah, 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 blah. Doesn't matter. We're going to leave it like that. And so if we go and try to isolate this for v, so we have ln of v plus g in absolute value bars equals negative t plus ln of g, okay? And I'm going to go ahead and move this ln to this side so that I can have ln of v plus g minus ln of g negative t. And that way I can write it as this. Ln of v plus g over g equals negative t. I'm allowed to do that, okay? This is just using the rules of exponents. And now I'm going to apply a I'm going to transform this into an exponential equation. So I have v plus g over g equals e raised to the negative t, okay? And now I'm going to isolate v. So v plus g equals g e to the negative t, and then subtract t. V equals g e to the negative t minus g. Is that right? I think I missed something. No, that looks right. Okay. Oh, and then that's our particular solution. So v of t equals g of e negative t minus g. Oh, I'm sorry. It was v naught. That's why I was so confused. V naught. No, okay. I got to start over. Sorry. Okay. So because I was using 0, that was assuming that we're starting from 0. Sorry. Okay. ln of v naught plus g equals c. Okay, so that is our c, which means that we actually end up with ln of v plus g negative t plus ln of v naught plus g. Now that is what we want to move on to the over to the other side. Ln of v plus g minus ln of v naught plus g, both in absolute value bars, okay? And then we get ln of v plus g over v naught plus g equals negative t, okay? It's at this point that we can transform this into an exponential equation. So we have v plus g over v naught plus g equals e to the negative t, right? Does that look right? Okay, good. So remember that the only variables here now are v and t. V naught is just the initial velocity, so we have v plus g equals v naught plus g e to the negative t. And finally, v of t equals v naught plus g e to the negative t minus g. Okay, wow, that's a lot, right? Here is the cool part. So notice that if we take the limit as t goes to infinity, okay, of v of t, what's happening? So the only part that t influences here is this decaying portion of the function, right? So e to the negative t, when you take that limit to infinity, it decays to 0. So it actually ends up just being v naught plus g times 0 minus g ends up being negative g. Wow. Isn't that crazy? So in other words, the velocity eventually settles on negative g, which is bizarre. And it seems like, why would it be that? And actually that is mostly an artifact of the fact that we chose very simple k and m. But if you're interested in playing with this yourself, you can use the original IVP, which has m and k in its full glory, and you can see how you'll get some cool relationships between the drag coefficient k and the mass m and g. And you'll see how the units all cancel out to give you the correct velocity. But in other words, this gives us a more realistic model for velocity. You know that when you drop something, it'll have a terminal velocity. And so this is the correct reflection of that artifact. Super cool, right? All right. So that's that on that. In the next section, we're going to talk about, we're going to revisit the population models.